Hi, Dr. P here, and in this lecture we will take a look at the Diels-Alder reaction. Um, and I'd like to go over an intro to the Diels-Alder reaction, which I'll just abbreviate as DA or XN. And we'll look at the components of the reaction, namely its mechanism, which is actually really simple. Mechanism, and we're going to need a diene and dienophile. And then we'll take a look at some stereochemical considerations. And then some regiochemical considerations. Okay, so let's see here. Why don't we start off with the basic Diels-Alder reaction? We'll have something that is a conjugated diene. So that's simply the diene. And then to this we will add something that will react with a diene, and we call that the dienophile. And in the presence of heat, we will get the following taking place. And I realize I cannot find my red pen. I'll be right back. There we go, that's better. And the way that I like to figure out what the product is going to look like and draw the mechanism is to draw in the new bonds. So we're going to get new bonds there and there. So we'll get a new bond between carbon 1, or let me say call this carbon 1, I don't know, carbon 1 of the diene and carbon 1 of the dienophile, and then carbon 4 of the diene and carbon 2 of the dienophile. We can go ahead and draw our curved arrows here to show the flow of electrons. And these dotted lines indicate our new bonds. So we're going to end up getting a six-membered ring. And so the Diels-Alder reaction is actually a great way to make rings, to make six-membered rings. So some things to note here. One is it's what's called a concerted mechanism. What does that mean? Well, that means it happens all at once. So we'll say happens in one step. So similar to how an SN2 reaction happens in one step. The nucleophile attacks and the leaving group leaves at the same time. Here, the electrons move, and it doesn't matter which way you draw the arrows, clockwise or counterclockwise, but the diene and dienophile react to make the two bonds, the two new bonds at the same time. Now, the Diels-Alder reaction is an example of a larger class of reactions called cycloadditions. And cycloadditions are one type of pericyclic reaction, and we'll talk in more detail in chapter 30, which we'll be looking at next. We'll talk in more detail about pericyclic reactions then. But I just want to mention that this is a what we call 4+2 cycloaddition. The diene here has 4 pi electrons, and the dienophile has 2 pi electrons. Now I know you're saying to yourself, wait a minute, I've got a CO double bond, those are pi electrons. Well, those are not participating in this part of the reaction. It is important, though, that we have something that is electron withdrawing, such as a carbonyl group, attached to the dienophile, or else the reaction won't go. Okay, so our diene is going to usually have electron donating groups. And our dienophile is going to have an electron withdrawing group or groups. Okay, and so some examples could be so our methyl is our electron donating group, which I'll call EDG here. We could have something like a methoxide. So OCH3, I've got an extra electron density in the oxygen. So again, that's our electron donating group. Electron withdrawing group is going to be something like our carbonyl, because again, this guy here is polar, so we've got partial negative on the oxygen and partial positive on that carbon. So electron density is pulled towards the oxygen. So this here is my EWG, is that guy. Other examples could be something like CN. Let's see here, what else could we have? We could have esters, OR, a variety of things. So these are all electron withdrawing groups. So it's important that your dienophile has an electron withdrawing group, and having an electron donating group on the diene can be helpful. It can make the reaction more likely. Perhaps the most important thing for a diene is the following. Let me find my paper here. And that is the diene must have the right conformation. It must be in S-cis conformation. Okay, now obviously 1,3-butadiene does not have cis or trans because the alkenes are terminal here, but we can orient it in this S-cis conformation. And this is what we need in order to get the reaction. If we're S-trans, we can't get it because these ends are too far apart. To react with the dienophile. Just kind of point to those ends there. So you can see those are just a bit too far apart to have that reaction. So for example, something that is permanently in the S-cis conformation, like cyclopentadiene, this reacts very fast. In fact, cyclopentadiene will actually react with itself, even though, so, you know, this could react with another molecule turned sideways, even though it doesn't have an electron withdrawing group. But if we had something like, let's say this guy here, this is going to be unreactive. via our Diels-Alder reaction. Okay. Should also note that we get a syn stereochemistry. And that is to say that cis and trans in the dienophile is preserved. So what would that look like? Well, let's take the simplest case here. So let's say we had this guy. Again, it's always helpful if you're trying to remember what things are going to look like. Draw in where the new bonds go, and then draw your curved arrows. And so I'll end up getting CHO, that's our CHO. And these guys are cis, so they're going to be cis in the product. If they were trans instead, it would look something like this. Oops, I forgot my double bond over there. Don't want to forget that. And I could get it adding in either orientation, so this way, or let me move that a little bit, there we go, or flipped over. So I would end up getting the enantiomer. Okay. Grab some more. Grab some more paper here, and let's examine the stereochemistry of the Diels-Alder reaction in a little more detail here. All right, so stereochemistry. So I had that it was a syn addition. So our cis and trans in dienophile is preserved. There's also something called the endo rule. Now, what do I mean by that? Well, let's say we had the following. Let's say we took our very reactive cyclopentadiene, and then we reacted this with that guy there. Forgot my little plus here. Plus. All right. So let me go ahead and draw some arrows. Boom, boom. So now what I would get is the following. If I'm looking at it top down, I'd have my new six-membered ring, but this CH2 would be sticking up, and this guy is going to be down. We'll also get the enantiomer because that guy could be flipped around. plus En. Or I could draw it a different way. So basically this is what it's going to look like. So I'm looking at it like this. So six-membered ring, this guy's coming out towards us. That's the CH2 in the middle. I have a double bond here, which I didn't show. And then this is my CHO in this case, which is pointing down. Now, pointing away from this shorter bridge, that's called endo, or being on the side with the longer bridge is called endo. Okay, so if I look at this here, let's look at it a little differently. Let's kind of look at it like that. There we go. So now I could try to draw this, and it would look something like this. So this is my bridge here. Okay, let me circle that in red here. That guy is that guy. And then my CHO is pointing down. So it would looks like this. Okay, and so where I have that gap there, that bond is actually this guy in the back here. It's going behind this bond here in the front. So it is helpful to be able to draw this type of fused ring, or rather bridged ring type system. I can even make that a little smaller gap there, so hopefully you guys can see that. Now this is in the endo position. So CHO is endo. And just to sort of help with, recognizing where they are, I've got my model here. And in this model, the red are the endo and the blue are the exo. So what that's going to look like is, let me draw this in black here. Boom, 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 boom. It helps when you make the sound effects. And so we'll have our exo in blue there, and then we'll have our endo, and coming back down there, behind there is our other endo. Okay, so these endo are on the opposite side from our one carbon bridge, but they're on the same side as the two carbon bridge. And there are some reasons for why that happens. Okay, and just to sort of go off on a little bit of a, not exactly tangent, because we'll revisit this next in the next chapter. But how do we get bonds to form? All right, how are these bonds going to form? Well, we need to have overlap of orbitals. And so we're going to have our dienophile and our diene. And let me zoom out just a skosh here. And what we need to have is overlap of the same phase of orbitals between our dienophile and our diene. So these guys are going to overlap like that. But there's also orbital density here, and there's orbital density on the electron withdrawing group. So it actually works better if the molecule comes in like this, so that any orbitals I have on this back carbon here can interact in a constructive manner with any orbitals back here, and so we'll get our new bond. So essentially what's going on is we have something like let's do this. Let's do another example. So I'm going to take my take this guy, and take my dienophile here, and I'm going to go ahead and react these. And you do need the heat that I've indicated here. That's actually important. So sorry I didn't mention it before. So what's going to happen? Well, here's my succinic anhydride. That's a double bond. I haven't drawn those or indicated those here, and there are double bonds there. But this guy's going to come in underneath. And so if it came in like this, I'd get the exo, but instead it's coming in like this, where these atoms, their orbitals can interact with these, and I'll get now my new bonds forming. So this guy comes in like that. I'll try to get everything on the side. It comes in like that, and now I get my product here, which is a little crazy, but it's going to look something like this. And I find it easier to draw with this sort of going to look like that, and I can add in my other hydrogens just to illustrate that, yeah, these hydrogens are in the exo positions, so the rest of this ring, what was the succinic anhydride, has, this is succinic anhydride, not maleic anhydride. Anyway, it's in the endo position. Okay, if I was going to try to draw it that way, that's a little trickier. CH2. And then these guys are going to be going down, so I would have to do something like, if I drew just straight lines there and I indicated my hydrogens were sticking up, then that would be okay. So definitely look at some of the practice problems. Let me zoom in here a little again. There we go. Look at some of the practice problems, because I will have not just simple Diels-Alder reactions where we're making one 6-membered ring, but you may have to worry about the endo versus exo. Now, if you're really interested in the Diels-Alder reaction, and you look up some stuff, you may find that the endo rule is not necessarily a hard and fast rule. We, however, are going to treat it as such. Okay, for the purposes of this course, it's best to just say we always get the endo product. It actually turns out that depending on what your electron withdrawing group is, you may get some exo product. All right, now I mentioned the endo rule. We have something called the pseudo-endo rule as well. I just put pseudo-endo in quotation marks here. So if I had the following. Okay, so here's my diene. I have a methyl group there that's cis here. This methyl group's trans. And I go ahead and combine these. What kind of stereochemistry does my product have? Well, what we're going to do is, maybe I'll draw this in green. We're going to pretend, is this green any better? That's kind of a dark green. Maybe I'll do blue. Sorry, pretend diene is a ring. And so in order to do that, I'm just going to draw in some dotted lines there. So we have an imaginary bond. So this guy is like, so what we're saying here is imaginary carbon. All right, so our methyl is actually where the imaginary carbon would be, our methyl down here, and this methyl is not where the imaginary carbon is. So in our product then, let's see, well, remember when I first drew this, our methylene bridge, the CH2 bridge, was sticking up. So the place where we say we have the imaginary carbon, that's going to be up. So this carbon here, that methyl, would be like so. This methyl is the other way, like so. And then this guy is going to be endo to this, CHO. Now, it could add the other way. This could be flipped over. It could also add from the other face. So we could get, so, you know, if I flip that guy over, I would get this guy, that guy. And I also, again, because this could come in from one face or the other face, I would get the enantiomers of both of these. So I could get quite a mix of products. So it can be a lot to keep track of. But definitely familiarize yourself with the endo rule. The text does go over the endo rule. The pseudo-endo rule is not really mentioned in the text, but it's something that I like to mention, so that way you keep all of your relative stereochemistry the same. Okay, because definitely when this guy reacts, these methyl groups are going to be trans to each other. And, for example, you know, my electron withdrawing group and that methyl group are going to be cis to each other regardless of the orientation. Okay, so that's the stereochemistry. Okay, we maintain cis or trans from the dienophile, that's maintained in the product. And then we also have to follow the endo rule and the pseudo-endo rule. Now, what about regiochemistry? Okay, so regiochemistry is as follows. So let's say we had, so let's say here, D equals electron donating group, W equals electron withdrawing group. So if I have my electron donating group here on the diene, and I've got my electron withdrawing group, and I add these together, I get the 1,4 product. Okay, not that guy. All right, so I'll just do a big red X through that. Similarly, if I have my electron donating group at the end, oops, do that guy up. They should be cis to each other from the pseudo-endo rule. We get the 1,2 product. and I'm not going to draw in the 1,3 product. Okay, so this is something important to remember. Sometimes it's called the pseudo-orthopara rule because it's sort of like a para position or an ortho position in a benzene, but it's not benzene. So you never get the 1,3 product. Or I shouldn't say never. You don't get the 1,3 product usually. So especially for the purposes of this class, we won't get the 1,3 product. Only 1,4 or 1,2. Why is that? Well, it has to do with the interaction between the electron donating group and how it affects our orbitals, and the electron withdrawing group and how it affects these orbitals. And basically, we want to get our extra electron density to line up with less electron density. So, you could, for example, draw some resonance structures with positive and negative charges, and your negative and positive charges should line up to show you how things would orient. If you really want to do that, I can take some time in lab or something to show you what it would look like. But I think it's easiest just to remember you don't get 1,3. You either get 1,4 or 1,2. All right, so if I gave you don't draw the 1,3 product, okay? Instead, flip it over when you go ahead to draw in your little mechanism there, and that's going to give us now that guy's there, CH3, and then I've got my CHO is there, and it could be either, either up or down, so you wouldn't bother to indicate it necessarily. You'd get a mixture of both. You would get a mixture of both. Okay? All right, so I think that's everything I wanted to talk about for the Diels-Alder reaction. Definitely try the problems. There are some practice problems and some end of chapter problems as well. Definitely worth trying. We'll talk more about this in the next class, the next in-person class meeting. And if you guys have additional questions, we can hopefully go over those as well. But being able to predict products of the Diels-Alder reaction with correct stereochemistry and regiochemistry is important. All right, well, that is it for this lecture. And so until next time, stay safe out there. Bye.